the switch to the ON position. There's only going to be two sizes of turbine engines on the test. They're either going to be small or they're going to be large. Yes, you're correct, Friedrich. If there's not an APU on board that aircraft, that means that you don't need pneumatic power to start the engines, which means what kind of starter is on the main engine? Electric, okay. On electric starter motors, the shaft coming out of the starter motor going into the engine, does that go in and out like it does on a reciprocating engine, or is that shaft always connected to the gearbox? It's always connected to the gearbox. So even if you let go of the starter switch, does the electric starter motor, is it still connected to the engine? Yes. So can you then, if you have a hot start or a hung start after you've let go, can you reapply and push your thumb back down on that starter switch if it's an electric starter motor? Yes. And that's the end of that. So, operation 1. So more engine operations. So you've got the engine started. Woo-hoo! It's got it accelerated to idle. You're a happy camper now. So now what are you going to do? You're going to start checking things. You're going to turn on the electrical generator, especially if it's an aircraft that has a small jet engine in it and you have a battery that started the engine, the battery that ran the starter motor. You're going to want to charge that battery up. If you have a bigger aircraft that has large engines, you may want to power a lot of things on board the aircraft. So in that case, you're still going to turn on the generator. It may be a big 400 volt AC generator, but in either case, you're very likely, once the engine gets running, you're going to turn on a generator. You're going to make sure that the RPM has stabilized. That is, it's not going up, it's not going down, it's not slowly creeping up, it's not slowly creeping down. You're going to look at the EGT. Has the EGT stopped moving as it's sitting there? Jet engines are usually very steady. If you look at reciprocating engines and you look at the RPM gauges, it's pretty normal for the RPM to go up and down 5 or 10 RPM and see that needle moving just a little tiny bit. But on jet engines, for the RPM, it doesn't move. It just sits there. Jet engines just run, and they don't change RPMs unless you do something to it. So you're checking for the RPM being stabilized, you're checking for the exhaust gas temperature being stabilized, and you're going to look at the fuel flow gauge. So here's a great example test question. Y'all are writing down these example test questions, right? Typically, turbine engines that propel the aircraft, that is not an APU, but turbine engines that propel the aircraft generally have a fuel flow gauge for the operator / pilot / aircraft mechanic to read, and it's on the instrument panel. True or false? It's true. The fuel flow gauge that tells you how much fuel is getting burned, that is, let's put it this way, I have never seen an engine that pushed the airplane around. I'm not talking about APUs. But the engine that pushed the airplane, propelled it, that engine's got a fuel flow gauge on it. I've never seen an aircraft, even the C-250s, the original C-250 out here, when it came out, I don't know if it was the late 50s or early 60s, it put out 317 shaft horsepower. Those helicopters they put them on, it had a fuel flow gauge. And if you take APUs out of the picture, that's a pretty small turbine engine. Only 317 shaft horsepower. But it still had a fuel flow gauge. I've never seen a turbine engine that didn't have a fuel flow gauge, except maybe an APU that didn't have a fuel flow gauge, but we don't care that much about it. Pilots don't care that much about APU fuel flow in flight, because you don't usually run them in flight. Now you check the oil pressure during start, And how far did it have to move during that 30 seconds? It's a really good test question here. It has to move. It just has to move during that first 30 seconds. Now that we've got the engine up and running, now we ought to take another look at it and say, hey, the engine's running. It's been going for 30 seconds or a minute or two. What's the oil pressure ought to be? Now, if it's a cold day and we're operating a reciprocating engine, a piston-powered airplane engine, and let's say it was this morning, I'm up at 1,700 feet above sea level. That's about 1,300, 1,400 feet higher than here. So it's about 3 degrees Celsius cooler up there. A little bit of frost on the hood, on the top of my car this morning. It was probably around -1 or -2 or -3 Celsius, or maybe 28 or 29 Fahrenheit. If I was going to start up an aircraft piston engine, air-cooled engine, and I started it right up, and 30 seconds after I look and the oil pressure starts to move, it may come up very fast because the oil's kind of thick because it's cold. But if I've let it run for 30 seconds or a minute and it's at idle, is it going to be a higher oil pressure or a lower oil pressure than if I had started the engine up when the oil was at 100 degrees Fahrenheit? It's going to be a little higher if the engine is colder. Once it gets running, it will take a little longer for the oil pressure to come up, but now it's going to be a little bit higher pressure because the viscosity of the oil is higher. It's thicker. The nice thing about turbine engine oil is that it doesn't change its viscosity that much even with temperature. It doesn't get much thicker when it gets colder. It doesn't get much thinner when it gets hotter. So that's generally not much of an issue on turbine engines. Now, if you look at cars or you look at reciprocating piston-engined aircraft engines, is it a good idea if you started it 30 seconds later, push the throttle all the way forward, and run it at takeoff power? It's not a good idea? Well, I think there's a better term, Friedrich, than heat shock, because there is a term called shock cooling on reciprocating engines. But there's a better term than word shock. So can anybody describe what's happening inside, say, the cylinder of a reciprocating engine that's air-cooled? Plane or helicopter engine. Made out of this metal? They all expand at the same rate? Are they, when you the engine and it's cold, have they all expanded to the size that's normal? No. So maybe some are still big and some are still small. Especially no. Cold, it's going to wear out the parts faster than it normally would. If you read reciprocating engine maintenance manuals and overhaul manuals, whether it's or generally say, even if it's cold, up between RPMs, even though it idles at 500 or 600. And then when the temperature comes up, and maybe the cylinder head temperature comes up, then at some point you're going to run the engine at a higher power setting. Turbine engines, on the other hand, this is not nearly such an issue, because what happens on the inside of a turbine engine when you turn on the ignition and you turn on the fuel nozzles? What happens to the temperature inside the combustion chamber? It goes up. Does it go up a lot, or does it go up real slow? No, it doesn't go up real slow. It goes up real fast. So how many of the engine parts are not pretty hot within the first 15 or 20 or 30 seconds? Very many. Now, I'm not going to say every part on the engine is up to normal operating temperature within 30 seconds, but a lot of it is. However, there could still be in the maintenance manual where it says that when you're operating this engine on a test stand, it may say, let the engine run at idle for a minute before you go to take off power, or it may say, run the engine at idle at a low power setting for 2 minutes before you go to takeoff power. Because every part, although it'll heat up faster than a reset, every part may not be completely at its normal operating temperature, even within 30 seconds. So how long you have to wait to go to takeoff power is probably going to be a lot less, but you need to make sure you read, if I'm doing engine runs and I'm trying to set the engine for takeoff power as soon as I start it, granted I'm getting paid by the hour, so I'm just going to eat a ham sandwich while I'm sitting in there waiting for, peanut butter and jelly sandwich. In any case, if the manual says wait for 2 minutes before you run it at a high power setting, so you're going to start it up and you're going to look at your watch and you go, okay, that's 4 bites on my ham sandwich if I chew it. And when you 5 bites, I don't know, depends on how fast you chew. Then at 2 minutes, then you could go to takeoff power, see if what you did fixed it. So there may be a warm-up period on a turbine engine. It's usually just a lot less time than it is on a reciprocating engine. So let's keep going on more checks here. Now granted, when you started the engine, hopefully you knew what the normal idle was, and you're going to check to make sure it came up to idle. But during start, you are kind of busy. You just want it to go up to about idle. Now that you've got the engine running, maybe you need to let it warm up for a couple of minutes. Now that it's at idle, you want to check, is it exactly at the RPM I want? It's generally going to be something plus or minus. It might say 50% plus or minus 1%. So that means 49% is good, 50% is good, and 51% is good. So that would be something you would want to look up before you go out to run the engine. Of course, I know Kittrick is going to take the entire 17 volumes of the maintenance manual out there with him to the aircraft in case he has to look that up, right? On your iPad. It'll be electronic versions on your iPad, right? Yeah, that'd be sweet. Okay. So you're going to make sure it is running at the correct idle RPM. And you may have to push it up off of idle and pull it back, and push it up and pull it back a couple of times. You may flip a switch in the cockpit to turn on the EPR probe heat. You might not. What if has anybody ever been to Minnesota? How about Wisconsin? Michigan? North Dakota? South Dakota? Pennsylvania? Anybody ever been where it gets cold and it snows and there's ice and sleet and hail and stuff like that? Okay, Montana in the winter. All right. So you may be operating a turbine engine when it's cold and there's frozen water particles in the air. You may need to turn on the EPR probe heat. Otherwise, you may run the engine up and ice might get stuck in the EPR probe and you won't get the correct EPR reading. So you might need to turn on the EPR probe. Hex, although it's not really a good idea while the engine is running to go grab the EPR probe to see if it's hot. I highly discourage you from touching the EPR probe while the engine is running. In fact, the EPR probe in the exhaust, it's also not a good idea to touch that when the engine is running. And along with EPR probe, if you're going to have to turn on the EPR probe heat, you're probably going to have to turn on the engine inlet anti-ice. Now, I've seen on smaller turbines, you don't have to write this down, on smaller engines this may be electric. On bigger engines, they usually take bleed air off of the engine and pump it to the airframe, they pump it to the leading edge of the duct, the leading edge of the intake. But where does that air go after it goes into that duct? It gets sucked into the engine. So if you're pumping hot air to the inlet duct and then that hot air gets sucked into the engine, what are you doing to the density of the air? Is the air more dense or less dense than it was before? It's less dense. So is the engine going to perform exactly the same? No. How about the fact that you're taking bleed air off the engine? Does that impact it? You need to be careful. If you turn on the inlet anti-ice, in particular, if it's using bleed air off of the engine, your engine gauges may move. You may need to know how much are they supposed to move. If I'm going to do takeoff power, if I'm trying to set takeoff power, with the anti-ice on or with it off, I may need to know two different numbers. What if I'm at idle and I turn on the inlet anti-ice? Does that impact the idle RPM? Well, what I mean is, if I turn it on, is it normal for it to go from normal idle to be 1% lower than normal? Well, you're going to need to look that up. Ashton. It depends on the fuel control. It depends on the engine. Yeah, you're right. Some engines, you may not notice anything, especially if it's an electronic one. It's like, you would probably see an increase in fuel flow, yeah. But it may be such a small amount you might not notice it. The point here is that if you're going to operate, first of all, with anti-ice, you may need to operate it if you're outside and it's snowing or hailing. And number two, now it's going to impact the numbers you see on the gauges and whether or not you think the engine is operating correctly or not. You may need to operate the reverse thrust or the thrust reverser. I had a job where I was traveling a lot on the airlines, and it was fun when I'd sit next to somebody. I could tell if they were maybe like not very happy about going flying because they were kind of scared. So I'd start telling them the story about how I have a master's degree in aviation safety, and I'm an airplane mechanic and a pilot. All these bumps and noises and clunks in the airplane, I know what all that stuff is. You see the air conditioning, you can hear the noise in the back, that's the APU going on. They're going to push us back. You're going to see the lights flicker as they change off of ground power to APU power, and then you're going to hear the engine start to spin up, and stuff like that. And they start believing me that I know all these things. And then after takeoff, of course, the pilots are going to grab the landing gear handle and lift it up. And especially if you're in the middle of the airplane near the wing, the landing gear are underneath you, and they come up pretty hard and pretty fast, and they make a pretty good clunk. And so what you do is, as soon as you get ready for it, as soon as it goes clunk, you reach over and you grab their shoulder and squeeze it as hard as you can, and you go, ah! And then they pee their pants. I'm just kidding. I would never do that to anyone on purpose. So you might want to, if you're going to run the engine, you might end up checking the reverse thrust. Of course, now you're not just blowing exhaust out the tailpipe, you're now actually blowing air forward. Of course, if you cleared the front of the engine to not suck up any foreign objects, it's probably clear to blow air forward. If you're operating a turboprop, if you're operating a turbine engine with a propeller, you're probably going to grab the propeller lever and move it. Whoa, and make it. And here's something we haven't talked about yet lately. Are y'all doing turbine engine gauges in another class? Okay, well, all right. Well, what's the nice thing about turbine engine? One of the nice things about turbines compared to recips is that they don't vibrate very much. Most of the parts that spin around in a turbine engine just spin around in a nice, perfect circle. They don't reciprocate and go back and forth. So they're much, 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 much smoother. Of course, now instead of running an airplane engine in a recip at 2,500 RPM or maybe redline at 2,700, even if it's a geared engine, it's probably not going to go past 32 or 3,500 RPM. Now we're talking about turbine engines. Even a PT6 goes like 12 or 10 or 20,000 RPM, maybe 30,000 RPM. So what do you think vibration is like in an engine that's spinning around at 30,000 RPM? You think vibration is good? You think vibration is bad? Does it not make any difference? Vibration can be very interesting. Question?
I think about it this way. I think it was last semester we had props, and Mr. Aspen brought out
the prop balancing device.
Yeah. And just to show how bad prop vibration was, like just one little tiny minuscule amount of weight in the wrong spot could destroy a prop or an engine.
Right. And that thing's going,
It's
right, that's going 1,000 RPM, 2,000 RPM. So my point is, especially when you get to the bigger engines, they're going to have vibration sensors bolted to the engine, more than one. It's pretty common to put a vibration sensor near the fan, and one near the compressor, and one near the turbines. Because that's where the biggest amount of weight, the biggest amount of inertia is. And then those sensors can be read inside the cockpit. So if you have a bigger aircraft, and certainly a newer aircraft, even smaller engines that are brand new, like a brand new medium-sized business jet, it's going to have vibration sensors on the engine that are available to see the gauge. And I got a picture here shortly that I'll show you. And of course, you're going to not just check at the top of there, is the engine running at the correct idle RPM? Can I get the power setting out of I want it? Obviously, if it's a turboprop, it's going to be torque. If it's a turbo fan, you're either going to be looking at fan speed or EPR. If it's a turbo shaft engine in a helicopter, you're also looking at torque. And of course, if you're operating the aircraft as a pilot, that's the power setting that that person is really interested in, because they want to know, can they get off the ground with a certain amount of runway that they have, with as much weight on board the airplane. So that means for mechanics, that's arguably one of, if not the most critical power setting we want to check. If the idle is off by 1%, no problem. But if it's 1% below takeoff power, then that means the runway needed is going to be a lot longer. So I think that was the last one there. Okay, so we've got 2 full slides, a million things to check. So of course there's 3 major power settings. Did I say EPR? I can't remember if I said EPR. So if you were going to set the power in a turbine engine, you're really looking at 3 things. And I've already talked a lot about engine pressure ratio. Torque is going to be found on turbo shaft and turbo prop engines. What kind of machines usually have turboshaft engines propelling the aircraft? Helicopters. All right. So fan speed. So let's say I got my big old fan here. Fan speed, I might have an engine that only has 1 shaft. So nobody's even going to call it N1 anymore. And in fact, it might just be the engine RPM gauge. And it might not say fan, it might not even say N1. But the bigger the engine, the more likely that there's going to be 2 shafts. So we're going to have our cardboard tube made out of steel. And it's going to have compressor blades on it. And it's going to have turbines that drive it. And then, of course, somewhere in here, we got to have a combustion chamber. And the way I remember which part is N1, N1, you see that little 1 right there? N1 tells me the first thing that the air hits, and everything that is connected mechanically to that all the way through the engine core. So if I look at this engine, there's an N1 and there's an N2. And here, I'll just draw the engine core here. But if I look at, let's try a different color. Let's try some blue, let's try green air. Nah, I don't like that green. Let's try light blue. So here's air, the first thing that the air hits. So that thing is N1. So in this case, the fan is N1. So now I keep following this air as it goes through the engine. And so this fan is connected to the first set of compressors. So this is also N1. And I'm looking at this shaft, everything bolted onto it. Oh, these turbines back here, those are the N1 turbines. N2. N2, that 2 tells me that it's the second thing that the air hits and everything bolted onto it. So if I've got N2, well, here the fan in these compressors, that's the first thing the air hits, pow. The air hits this second compressor, that's the N2 compressor, and the air keeps going. Wow, look, it's hitting something that's bolted onto it, so that's the N2 turbine. So in this case right here, we would have 2 RPM gauges on this engine. If there's more than one shaft that is spinning around, there's going to be more than one RPM gauge. And we could be labeled N1 and N2. N1 is also what the fan is, so this could also be labeled the fan. So is the fan ever going to be N2? No, it's not, because the first thing the air always hits is the fan, if it's a turbofan. And of course, we've talked about EPR quite a bit. Does anybody have any questions about the difference between fan RPM and N1 RPM? About what part of the engine is the N1 spool and which part of the engine is the N2? To write this down, Pratt & Whitney and General Electric, even on their big engines, they on an N2 and do N2 and N3 for quite a while. What I like about this following answer is that the answer is the same for turbines and for reciprocating engines. Let me rephrase that. Let me back up. High power reciprocating engines and turbines, there's usually a limit. How long can you push the power lever all the way forward and keep the engine at takeoff power? Generally, it's a maximum of of what? Oh, no. 5 what? 5 seconds? 5 hours? Huh? 5 minutes. That is correct. Generally, this is a great test question. Thanks, Amir. I think you'll get this one right. Generally speaking, turbine engines have a maximum takeoff power setting of 5 minutes. You can't run it at takeoff power for more than 5 minutes. And it works like this. Anybody ever take off in a jet airplane? In the back seat? You're in the first class, you're drinking your margarita, and back in the economy, they're looking through the curtain, wishing that they had a margarita. Okay, I'm the only person that sits in the back and thinks about that. So the pilot shoves the power levers all the way forward on takeoff, and the engine goes to takeoff power. They let go of the brakes, and they roll down the runway. We'll say it's a 737. It rolls down the runway. It takes about 20, 30 seconds. It lifts off the ground. The pilots will put the landing gear up. They'll start putting the flaps up, and then they'll grab the power levers, and they'll pull the power levers back to what's called climb power, and that's less than engine is at takeoff power is usually much always noticeably less than 5 minutes. I'm not going to say a number because I don't want to confuse you, but usually not even half of that 5 minutes, maybe only a third of it. But they could run it up there and leave it up there for 5 minutes. As long as you pull the power back just before you get to 5 minutes, now you can shove it back up again. But generally no reason to do that in turbine-powered aircraft, because turbine-powered aircraft, if one turbine engine goes out, the other engine has so much power, you're still climbing even at a climb power setting. The next power setting is called maximum continuous power. So for fun, let's just say that we're going to use fan RPM as our power setting gauge. So there might be a takeoff power, and we'll just say for fun that that's at 100%. Then there might be another here, and it might be maximum continuous. And here's this interesting word that nobody wants to spell on the test. 2 U's and 2 O's and 1 I. Maximum continuous. Continuous means it doesn't stop. Maximum continuous power is the highest power setting you can run the engine at, and there's no time limit. You can leave it there continuously, hence the term maximum continuous. So in theory, operating the engine out, test aircraft, and you're doing some kind of a power run, you take off power. How soon before you have to pull the power lever back? Generally, no more than 5 minutes. You're going to have to pull it back, but you could pull it back continuous. And how long can you leave it maximum continuous? Run out. Yeah, there's no time limit. There's no time limit. I'm not going to ask you this on the test, so I don't recommend you write it down. But there are very few engines in here I've seen that have a 30-minute power setting that's higher than max continuous but lower than takeoff. But that's only a very, very few engines. I'm not going to ask you that on the test. So I'm going to cross that out. The point I want to get across here is that these power settings, you need to know what they are. Now, it's not likely that you're going to go out and run the engine and sit there and push it up to takeoff power and then just start eating your pastrami sandwich with onions and pickles and hot mustard and just sit there and exceed that 5 minutes. Me personally, I can eat a pastrami sandwich way faster than 5 minutes, so that's not a problem for me. But some of you might eat slower than I do, and it might take you 6 or 7 minutes to eat that sandwich. I'm making a joke. Generally speaking, if you're doing engine runs, you're going to go to max continuous power, and you might leave it up there for 30 seconds. And you've checked everything you want, and you're going to pull it back. You're probably going to pull it back to idle, but you could pull it back to maximum continuous and then just leave it there. Again, though, and if you're not flying the aircraft and you're on the ground, how long would you leave it at maximum continuous? Just as long as it took to do whatever checks you needed to do. But I want you to know more than the average pilot knows about turbine engines. Anybody have any questions about max continuous power or takeoff power? So here is a power gauge. You do not have to draw this on the test. This is a torque meter out of a helicopter. You'll notice that there is a red line. You know, there's a yellow arc and then there's a green arc. So you can see the red line right here. You can see the yellow arc goes all the way there. It looks to be about 85 or 86, I'm not sure. And then the rest of it is a green arc. So generally speaking, if you see a yellow arc, that means there is some condition under which you can't operate there. Or there's some condition you can only have that happening to operate in there. So this might say something like, don't operate in the yellow arc for more than 30 minutes. And that would be pretty common on a helicopter engine, because helicopters, once they take off, they don't need as much power. But if they're holding an air conditioner and they're going to set it down on top of a building, you don't have to remember this, but helicopters take more power to hover and not move than they do to fly forward. So if they're at gross weight, maximum weight, because they're carrying an air conditioning unit, and they have to hover above a building, they might have to go into that green arc. Do you think they might have to hover there for more than 5 minutes? Maybe. So that one of those things I'm not going to ask you, that 30 minutes, that's generally going to be found on helicopters because they may need a power setting that's not takeoff power, but it's pretty close. And of course, helicopters are turbo shaft engines, and turbo shaft engines, you set the power with the torque meter. There's a percent RPM gauge. This is what normal non-electronic RPM gauge. You notice there's a little tiny spinner needle over here that spins around. So when this needle comes up to 10, this needle will have spun around once. Because this needle might not be that accurate. These are really old style gauges. So this might read 9.5 or 10.5, and you're trying to figure out, okay, is that 9.5 or 10.5? And you can accurately read it here. Of course, the engine's not going to idle in our aircraft. At 20%, we're going to turn the fuel nozzles on. Correction, we're going to turn the ignition on first, then the fuel nozzles to on. The thing's going to light off. We're going to hold the starter motor down until we get to 40%, and then we'll have been past the self-accelerating speed. The engine will accelerate up to idle, and our engine is 50. You notice there's a yellow arc here. It's possible that this yellow arc is due to some weird vibration on the engine that only occurs between 75 and 84%. So that if you see a yellow arc on a gauge, you need to look that up and say, oh, when can I operate in it? And I've seen this on a very, very few jet engines and a very, very few reciprocating engines where it'll say, operate the inside arc. Push the throttle forward and go through it as fast, almost as fast as you can, or pull the throttle back and go back down through it, but don't leave the engine running. So that would be something you, on this engine, you'd want to look and say, well, when can I be in the yellow arc? Can I hang out there? Can I let go of the throttle and eat the rest of my sandwich? Or do I need to push the throttle forward and get into the other green arc? And you'll notice this red arc, this red line, is it exactly at 100? It looks like it's at 99. Is that okay? Yeah, of course it's okay. We just know in general, turbine engine RPM gauges, red lines are at 100, approximately or near it. Here's an EPR gauge. Now there's actually a knob right here, and that actually moves this needle. What you would do, or what a pilot would do before you run the engine, is you'd look up the outside air temperature and the outside air pressure and say, on this day, with this atmospheric conditions, what would be takeoff power? And you would rotate that knob and you would set it. In this case, it looks like if that's 2.1, 2, 3, 4, 5, 6, 7, 8. No, that's, so these big lines must be, that's 2.1, that's 2.2. That's 2.3, that's 2.4. So this needle right now is set to about, see if that's 2.4, that's about 2.44, okay. So you would set that before you started the engine, and then when you started the engine, I guess you could set it after you started the engine. Then when you push the power lever forward, of course this engine is, if this is at 1, that probably means the engine isn't running. So this is going to spin up, and when you want to go to takeoff power, you align the two needles. And when the two needles are aligned, you know you have takeoff power. It's really not there for mechanics, it's there for pilots, but we can use it. That way, when they're on takeoff, all they have to do is just push the lever up until the needles line up, and they know they're at takeoff power. Here's a fuel flow gauge. It's kind of hard to read it, but it actually says pounds per hour in there. You can't see that one, and it's hard to read it in there, but that actually is 1,000. Whoops, not 10,000. So this is actually set to 1,000 pounds per hour. So if the needle was pointed right here, that would be 3,000 pounds per hour. And it goes all the way up to 12, although the engine probably doesn't do that. There was an airplane I used to fly on. I sat downstairs, and the engines at takeoff, at normal cruise, would burn about 10,000 pounds an hour each. Now that must have been takeoff power. That must have been takeoff power. 8 engines, 10,000 pounds apiece, 80,000 pounds an hour. But then, after takeoff, you pull the throttle back. So there's pounds per hour. I know these pictures aren't that great. These are the 6 main gauges on a Pratt & Whitney PT6. So the interesting part here is, look, here's a torque. What I find interesting, and you don't need to write this down, but it looks like there's 2 red lines on this torque meter. I don't, well, good. I appreciate your logic process. Ashton? No, my guess is, and I'm not an expert on PT6s, is that this is one that they decided to put one red line on there for takeoff power, and they decided to put a red line for maximum continuous. That's my guess. but I do appreciate everybody's thought process. In any case, what I do find interesting, this says ITT, and that means intermediate turbine temperature. It means on Pratt & Whitney PT6s, they don't put the EGT gauges after the last turbine. They actually stick it between the turbines, hence the ITT, intermediate, in the middle of the turbines. This actually does have 2 red lines marked. This one right here is the red line for all other operations. And here, look at this big old honking flag. They really don't want you to notice that that's the EGT red line for start. They don't want you to forget that that's the EGT red line for start. So if torque sets power, and in a PT6 there's 2 separate shafts spinning around, right? It's got a free shaft, or the power shaft is not connected to the gas producer. So the propeller, that is connected to the power turbine, so you only need 1 RPM for it. And then here, it's hard to read that letter, but that's actually NG for gas producer. And that's the compressor and the turbines that drive the compressor. But that's not telling you how much power. In this case, it's a turboprop, so the torque meter is telling you how much power. But as you're advancing the power lever, you're also going to want to be looking at the EGT. And generally speaking, in turbine engines, the higher altitude you go, the engine has to work harder to compress the air because the air is thinner up there. The air is less dense. So generally speaking, as you climb up in altitude, in order to maintain this torque, you climb up a few thousand feet, the torque's going to go down, so you push the power lever up, but as you push the torque up, the EGT is going to rise a little. And then you climb up some more altitude, and the torque goes down, so you push the power lever forward to get the torque to come back up, and the EGT rises. At some point, at some altitude, you're going to hit the EGT red line, and now you can't push the power lever forward, even though you're not producing maximum torque anymore. This is called being temperature limited. Ashton. Yes, it's very possible that you could hit an RPM red line. Most of the time, under this sort of situation, as you're climbing in altitude, you're going to be temperature limited. You're going to hit your EGT red line, and you won't be able to maintain full torque, and you'll probably hit that EGT red line before the RPMs red lines. But yes, your RPMs would be going up because the compressor is going to have to work harder. And the only way it can work harder is to spin faster. The problem is, to spin faster, we now have to extract more energy. We got to burn more fuel just to do the same amount of compression. This also might be the case if you're operating at a Phoenix International Airport and it's 115 that day. You may take that Southwest 737, Southwest Airlines 737 out on the ramp to do an engine run, and you may find that you get to the EGT red line before you get to the power setting you're looking for. So that temperature limited. In fact, that is just such a great test question right there. That's where you had EGT red line. Before hitting takeoff, before hitting desired power. Because you could be temperature limited on takeoff. You also might be temperature limited in flight. Most of the time in the aircraft, you as the mechanic aren't going to be in the aircraft when it's temperature limited. Because most of the time this happens is when the aircraft is climbing up higher and higher and higher. The only time you would probably notice this as a mechanic, unless you're going along for the flight, the most likely the time you would notice this is when you're running the engine on a really, really, really hot day, which in Fresno, it cracks 100 in the summer, right? Does it hit 105 very often?
Yes.
It's possible that you might hit a temperature limited situation doing a full power takeoff run in Fresno on a really, really, really hot day. And with that, we're done for today. Question, Elizabeth?
So on the
Yes.